So the first of our electrophilic substitutions is going to be called nitration, but that is not the name of the mechanism. Remember, the name of the mechanism is electrophilic substitution. The reagents, concentrated nitric acid and concentrated sulfuric acid, are going to be mixed together with each other. And the sulfuric acid is going to be acting as a catalyst, and the nitric acid is going to provide us with the N and the O2 for the nitro group. The conditions, it's one of those ones that we're going to have to learn. It's 50 degrees C. So what does our overall equation look like? We're going to take our benzene ring and we're going to add the nitric acid. Remember, the sulfuric acid is a catalyst, so it's not going to appear in the overall equation. It's going to appear in the mechanism, but not the overall. I'm going to swap out one of the H's for an NO2. And then, what's our other product going to be? Because the H has fallen off, but there were some other bits from nitric acid. See if you can balance that equation with the other product. Should have got water. Can you name the product? So how does that mechanism work, and how do we get that product from those reactants? Well, the first thing we have to do is figure out what the electrophile is, what the thing is that benzene's going to attack. It doesn't seem to attack the whole of nitric acid, it attacks part of it. And our electrophile, when we're doing benzene reactions, one of the easiest things you can do to figure it out is put your hand over the benzene ring. So just cover over the benzene ring with your hand and look at what is left. So imagine that this is your hand. Cover your hand over the benzene ring so everything in the box is hidden. What is left? That's your electrophile. So your electrophile is NO2, and where it attached to the benzene ring, which was via the N, that thing has got the positive charge of an electrophile. Okay, so cover over the benzene ring with your hand and have a look what got added. Put a plus on the atom that is joined to the benzene ring, and that is your electrophile. So how do we generate that electrophile? How do we make that from our reagents? How do we take nitric acid and sulfuric acid and generate that? Well, those two react together, and bizarrely in this reaction, sulfuric acid is going to act as an acid, but nitric acid is going to act as a base and accept the proton. And what happens is it kind of happens in two stages. So it's not the final answer yet, but we're going to move a proton from the sulfuric to the nitric. So we end up with H2NO3+, and we lose it from the sulfuric, like that. But this thing on the left with the added proton is not stable, so it doesn't hang around like that. So then that thing is going to fall apart. So it's going to break down and give me water and the NO2+. So in the exam, we would remove this part, and we'd just be left with this bit. So that would be our balanced equation. Okay, so we've got water and NO2+. Remember that this is our electrophile. So then what happens in the electrophilic substitution bit? So when you're asked for the electrophilic substitution, this is what we're doing. We're going to take this and we're going to use our electrophile and put the plus on the thing we're going to attack. This time I'm going to add it to this position down here. So I'm going to make my curly arrow come out from the pi bond, so starting touching the ring, not in the ring, touching it. I'm going to come out from this area, the bottom, and collect my electrophile. So I stuck on the NO2, but I've still got the H on there. Now remember, it's going to use 2 electrons from the pi bond, and the pi bond is then going to be extending over the remaining 5. So draw this imaginary line. You can't have that in your final answer. Draw this imaginary line. Think about it, or put your ruler there to stop you from going beyond this line. So you can imagine having your ruler there, stop you going from beyond that line, and draw the broken pyramid, this kind of horseshoe. So it must extend to from the 5 carbon atoms that are either side of where you've put your nitro group in this case, and then you've got a plus charge. And then this H is going to reform the pi bond by being substituted. Like that. And this is our electrophilic substitution. So once we've done that, how do we get our catalyst back? Well, this H plus that we generated at the end of the mechanism reacts with the HSO4 that we created when we generated our electrophile, and it reproduces our sulfuric acid. That's our mechanism for nitration. What I want you to have a do now is see if you can write a balanced equation for this reaction for nitromethylbenzene from methylbenzene. So start with methylbenzene, draw that on the left, draw 4 nitromethylbenzene on the right, and see if you can work out a balanced equation. So I've drawn those two structures, methylbenzene on the left, 4 nitromethylbenzene on the right. I know that we use nitric acid, the sulfuric is a catalyst, and to balance that we would have water at the other side. So how does that happen step by step? And it says outline the mechanism, that's the electrophilic substitution part in the middle. But it does say include the role of catalyst, so we've got the beginning and the end. So the first step is generate the electrophile. So take your nitric, mix it with your sulfuric, and generate that electrophile. There's my electrophile. Now take my electrophile. Now the key thing to this one is we're very specifically being told where to put that nitro. Well, we've been told put it at number 4. So look, I'm going to draw it right down here, and to make sure I get it right, I'm going to start at my pi bond and I'm going to go out of my ring via that position number 4. So I've put the NO2 on and I've still got the hydrogen. So remember I'm going to put my imaginary line, or I'm going to use my ruler from position 1 to position 5, so that I can, 2 to 5, so that I can miss out those. I'm going to make my horseshoe open where I need it to be open, in line with where my substituents are, and put my plus on. And then it's going to be curly arrow back in to get rid of the H. And there's my electrophilic substitution to make that 4 nitromethylbenzene. And then at the end, that H plus is going to regenerate that catalyst. We've got electrophilic substitution. And it's actually only that middle line that's the electrophilic substitution. The other 2 lines at the beginning and the end are about the catalyst, making it and then regenerating it, making the electrophile and regenerating it. Is there any other possible nitration products? So if I start with methylbenzene, was there anywhere else I could have put the nitro group? So I started with methylbenzene. Was there anywhere else I could have put the nitro group? So I'll pause the video and have a think what you might have got. So you might have got one of these two, 2 nitro and 3 nitromethylbenzene. But you could also have got, after one reaction happened, what's to stop it going again? So what if it went there and there? Or other multiple nitrations. Could have gone in 2 places, it could have gone in 3 places, it could have gone in places that were next to each other, in places that were spread out. In fact, it is this product, the 2,4,6-trinitromethylbenzene, that is the most likely. If I tell you that the old name for methylbenzene was toluene, this methylbenzene, and now I've got 3 nitros, trinitrotoluene. So tri-3-nitrotoluene, this is the structure of TNT.